Hello students. In this lecture we shall be discussing about the distinction among the different types of devices. Namely, we can divide the devices, nano-electronic devices, into three broad categories. That is quantum dots, then resonant tunneling devices, and second electron transistors. Now we must admit that the factors determining the energy of electrons on a small island are somewhat more complicated than is explained above. Now, so basically we are more focused on the energy of electron inside an island. This is what is the main factor determining the behavior of the devices. Now, to begin with, since an island may have different dimensions along each side, x, y, and z, the electron's energy levels may be quantized separately in each direction. So, you can have three directions, x, y, and z. So, quantization in these three directions will be different with a gap of, let's say, delta epsilon x, delta epsilon y, and delta epsilon z. These are the spacings between the quantized energy levels. Spacings between the quantized energy levels. Now, this delta epsilon, this value is calculated for, let's say, for an electron on the island, ignoring other repulsive interactions that can occur when more than one electron resides there. We consider that only one electron inside the island. This is a hypothetical case. Now, in fact, an extra n plus 1 electron attempting to enter the island needs an extra energy to overcome its electronic repulsion with n electrons already on the island. So, if, let's say, there are n electrons inside the island and one more electron, that means wants to enter, then it has to overcome the repulsive energy. This energy of repulsion or charging is given by U. So this energy of repulsion or charging is actually U. Now the total difference in energy between the lowest quantum state of an island with only n mobile electrons and the lowest quantum state for an island with n plus 1 mole electrons is the sum of U plus delta E. So naturally, uh, the lowest of the energy of the n islands, the lowest energy in this state, and if we add it up one electron, it becomes n plus 1 electron. So the lowest energy in this state, the difference between this one and this one is actually equal to U plus delta epsilon. Now the requirement of the additional amount of energy beyond the charging arises from Pauli's exclusion principle. So this extra delta epsilon energy, it is arising due to Pauli's exclusion principle, that no two electrons can have all the similar quantum numbers, or all the quantum numbers of the two electrons cannot be same if they are residing on the same energy state. So now this U and this delta E that we have understood, this U and delta E, their values also depends upon the size of the island. For example, if the island is short, the short dimensions island will have larger delta E will be high. It implies that more strongly quantized means if the island shape is like this, example, we have energies like this. If you reduce island shape, automatically the gaps increase. So this is delta E, and let's say here E1, and let's say here it is delta epsilon 2. So delta epsilon 2 is always greater than delta epsilon 1, and if we take say D1 here and D2 here, so D2 is always less than D1. Now so mathematically we can say that delta epsilon varies, or you can say is delta epsilon is proportional to 1 by r squared, where r is the shortest distance, or the shortest, let's put it as delta E proportional to 1 by d square, where d is the shortest dimension of the island. Now, shorter dimensions and smaller islands also increase U. So it's not only that delta E is only thing that is increasing with respect to delta E, it's also U will also increase. The charging energy will also increase. But it is little different, because we say that U grows large as the mean distance between pair of more electrons on the island grows small. So it's not the D that actually will increase U. You can say it's you can call it as R, or where R stands for uh, the mean distance between pair of mobile electrons. Mean distance between pairs of mobile electrons. That means as electrons are squeezed together, U increases. Now, thus, since the relative magnitudes of U and delta epsilon govern device behavior, and the Allen shape strongly influences the relative magnitudes of these two energies, Allen shape is a convenient basis of distinguishing these three categories of solid-state non-electronic devices. So the Allen shape is a convenient basis for to distinguish the three categories of devices.